Hello, everyone. Today we're going to present our presentation on trustworthiness analysis of Bitcoin OTC users. Let's first explain the data set we are using. So this is a who trust whom network of people who trade using Bitcoin on a platform called Bitcoin OTC. Since Bitcoin users are anonymous, there is a need to maintain a record of users' reputation to prevent transactions with fraudulent and risky users. Members of Bitcoin OTC rate other members in a scale of -10 to +10 in steps of 1. This is the first explicit weighted sign-directed network available for research. And the shape of the network, shape of the dataset looks like this. There are 4 columns. The first is source, which is the rater, the target, which is the ratee, and the rating, and the timestamp. So there's another paper called Temporal Evolution of Weighted Sign Networks done by Stanford, also evaluated this particular network. What they are focusing on is to identify the fraudulent users. Partially of our research was based on their result, but we are focusing on a different goal, which is give a newly joined user who does not receive any ratings from others an estimate goodness score based on our algorithm as soon as their first rating is made. And we did some preliminary analysis of the network. You can see in the first chart, the distribution of all the ratings. You can see that if a user find another user is trustworthy, they will tend to give it a score between +1 to +3. If the user find another user is untrustworthy, they will give them an extreme score of -10. And the second chart shows the distribution of the degree centralities.
Yeah, so basically we define a goodness score. So a goodness score is based on the average rating the user receive from other users. In that case, we also look at it normalizing by the ratings per day that an user receives. As you can see, the equation for the rating is below. Basically, we use 4 different hyperparameters, alpha, beta, gamma, and kappa to control the score distribution. And using this formula, we generate a goodness score at each timestamp on a per day interval for each user. And as you can see, we have an analysis of our goodness score. On the left, we see a distribution of the goodness score. In this case, notice the score is between -10 and 10, like the original data set. In our internal algorithms, we use -1 to 1, as shown by the graph on the right. But here, I just want to reconstruct it to the original algorithm purely for visualization purposes. As you can see, most of the users are considered relatively good, or at least unknown in this case, with very few users considered bad, but also very few users exceeding the 10 scale, which we think is normal. Furthermore, looking at the average goodness over time, as you can clearly see, the average goodness tends to stabilize, and this leads to a very stable network at around 0.5 to 0.6. This also makes sense as we believe the average user does tends to be good. Furthermore, looking at the quartile of goodness over time, the average quartile goodness, as you can see, is quite good. Even the first quartile goodness and the third quartile goodness are quite high, even though the minimum goodness is very low. And looking at the individual goodness over time, as you can see, the goodness score changes significantly throughout the network for each individual users, although you can see there's a lot more relatively good user than bad user.
So the second metric we looked at is fairness. And let me walk through how we came up with this measurement. First, we have a value called mean of U VT, and this is the average rating of a node V. And how we came up with this is we take all the in edges that V has, and we take out or remove the particular score that a node U has made on it. And so with this, we can then develop a closeness value. And this means if we have a node U rating on V, we take the score and we minus it. We find the absolute difference between that and the mean score that V has. And this can range from 0 to 2 due to our score normalization. And that means if we take 1 and we subtract this term, then we get 1 if it's perfectly close, and -1 is if it's completely not close. And so then we can finally arrive at the fairness score of a node U, that being the average closeness of its all of its rating up to a time point t, and we control the distribution with hyperparameters alpha, gamma, and beta. So next, we can look at the analysis of the results that we have run on our network. So after the entire time epoch, we see that the distribution of the fairness score is sort of tending towards positive. There's a lot of clusters around neutral 0 and around 0.2, but the average tends to be around 0.24-ish. And so the average fairness also starting at 0 over time tends towards positive. And we think this makes sense because in the transparent network where people see everyone's rating, people tend to only deal with others who are deemed trustworthy by the community. So next, we can dig deeper into the fairness score and see that if we look at the quartile fairness, then over time, even if the minimum dips below 0.2, -0.2, the first quartile to the max all tends toward positive. And the interesting thing is, if you look at the individual fairness over time, you see that those who are negative, they tend to dip and then stop moving, which means that other people stop transacting with them. Whereas the average users whose positive fairness, who has positive fairness score, they tend to become more and more fair over time as they deal with other people and give more ratings to other users. And yeah.
And besides the goodness and the fairness score, we also have a metric for the anomaly detection. So as a metric that being introduced previously, the number of ratings a user give per day. So the mean of that number is 1.2 for a particular user, and the standard deviation is 5.53. So what we define an anomaly behavior is when a user gives the number of ratings given in a particular day is greater than the mean, which is 1.2, plus 3 times the standard deviation, which is 5.53. And also, meanwhile, the fairness score of that person during that particular day is also less than -0.1. We define that user has anomaly behavior. So based on our metric, the total number of the user in the data set which has anomaly behavior is 14.
Yeah, and then we look at predicting a new user's goodness score when they first join the network with no prediction. So basically, we use 2 different hyperparameter, alpha and beta, to weigh the fairness score of the user rating the new user and weighed by their weighting. Using this algorithm and dividing the prediction into 3 categories: good, not good, and unknown, just like the similar to the original Stanford paper, we were able to achieve an accuracy of 0.96 on a test set. And thank you for listening to our presentation and reviewing our project. We really enjoyed our time working on this.